Okay, everybody, lecture 3 of 3, nuclear transmutations. Transmutation's a pretty cool word. I didn't make it up. I didn't make it up. Somebody else made it up. What a transmutation, if you break it down, mutation always makes me think of superhero movies, but that's okay. Nuclear reactions that are induced by striking a particle with a neutron or another nucleus. That's a nuclear transmutation. A nuclear reaction that are induced by striking a particle with a neutron or another nucleus. So here's an eraser. See if I can stand it up where you can see it. Probably not. So I have to hold. There's my eraser. It's going to sit there. Till I do something to it, it's going to sit there. So, transmutation. I had to hit the eraser for something to happen. It didn't just like hop out of my hand. So we're going to look at the particles we've talked about before, because it might have been a while since you've seen the last one. I don't know. So down my list. First one's a neutron. Second, alpha particle. Third, positron. Down my list. The P is proton. My negative charge shows me electron. I had to think when I saw positron. I was like, that's an electron, but not quite right. And I remembered. Positrons are electrons with negative charges, with opposite charges. And my hydrogen with 1, 1, we didn't talk about that one, but if you remember, a naked hydrogen is just a proton. We talked about that with acids and bases if you've done that. Like the alpha particle is naked helium, a proton is naked hydrogen. Nuclear transmutations can be diagrammed in sort of a condensed format. I like this picture from the book because it showed exactly what was what. Outside the parentheses to the left is the nuclide you start with. The particle that hits it is next. So those are your reactants at the left. I like it. So my products must be at the right. After the comma, another subatomic particle, and a product nucleus. That's what I make. So if I read that left to right, nitrogen, helium for my alpha particle, yields, and I switch those orders. A lot of times you'll see the product nucleus written before the ejected particle, even though it's not in the transmutation diagram. It doesn't matter. Like any equation, it's the same thing. And notice that the subscripts and superscripts add up to the same on both sides again, which is awesome. So if you want to try figuring out what particle is emitted in that transmutation, go for it. Hit pause, I'm going to do it. So I got 27, 13, aluminum. That's a stable nucleus. That's periodic table ready. So I must have to do something to it, just like the eraser sitting on the desk. So it says I hit it with a neutron. Mass, no charge, neutron? Yeah. So what am I going to release to make some sodium that looks messed up, because sodium is not 24 on the periodic table? Well, if this adds up to 28, 27 plus 1, 24 plus 4 is 28. 13, and then 11, and 2, and then helium. Very good. So, what we've got there is an example of a transmutation reaction. You've got 21, 27 to try here. So, 252 plus 10 is 262. On this side, I have 3 times 1. So, 262. What would I need to add to 3 to get that? That's a pretty big number. I think 259 plus 3 works. And down here, 98 plus 5, 103. That's Lawrencium. It's down at the bottom of your actinides, all the way over to the right. So that's how you do this. That's the first one from 2127. Please give your practices a try, and I'll post the answers. And then from there, all of a sudden, we go into brand new notes under that with no heading. What's a particle accelerator? Good. A particle accelerator, and this killed me, right from the text, device that accelerates particles. No kidding. So what else? Device that accelerates particles for collisions by using strong magnetic and electric fields. So it's for something. It's not just a device that accelerates particles. This is how you make man-made elements. You run them around an accelerator and you collide them together. This is how you induce these transmutations. Run the particles around, collide them together. Reactions with neutrons don't need an accelerator because neutrons have no charge. You can't use the magnetic and electric fields to move a neutron since it's not charged. Above what atomic number have the elements been made by nuclear transmutations? Above number 92. So for your rates of radioactive decay, next page. Radioactive materials that are found naturally decay slower than man-made elements. So natural elements, things that just are out in nature doing their thing, not things we made, time check, decay more slowly than what we make in lab. Your half-life is the time taken for half a given quantity of a substance to react. It's the time taken for half a given quantity of a substance to react. So if I have one half-life, however long it takes, I've got 50% of my original radioactive nuclei from one half-life. If I've got two half-lives gone by, I have 25% left. If I have three half-lives gone by, it's 12.5% of my original sample, my original radioactive sample that went away. The book, this kills me. What time lengths? A half-life is as short as millionths of a second and as long as billions of years. A way to be vague, but it's true. Half-lives take a lot of different number of times. There is still stuff decaying that was made whenever Earth was made. It's still going. There's stuff in lab that we're like, there it is. Oh, there it was. So, rates are very different. Radiometric dating is the method of dating objects based on their isotopes and isotope abundances. Method of dating objects based on isotopes and isotope abundances. So carbon-14 is the big one for archaeology. It's the big one for, I'd say, decently recent human history. Because carbon-14 decays in 5,715. 5715 years. So, if I find an archaeological object and say, oh wow, fortunate me, there's exactly half of the carbon-14 present. Mass spectroscopy would do that because you can tell how many atoms have what mass if you look from a mass spec. So you run that, compare it to what it should be, and you go, oh, half exactly of them are gone. This should be around 5,700 years old. You're never going to get exactly half, but that's my example. As you get down to the piddly amounts, you start to run out of accuracy. The oldest object that can be dated accurately doing this is around 50,000 years, 50,000 years. That's not bad. That covers a lot of human history. So these two questions, we'll just do them. It takes 5.2 minutes for a gram sample of francium to decay to 0.25. What's its half-life? Right off the bat, I noticed that the percent that's left is 25% of my original, from a gram to 0.25. It takes two half-lives to be down to 25%. So if it's been 5.2 minutes, half of that is each half-life. So 2.6 minutes. 2135, sort of putting the cart ahead of the horse, depending on when we do this in the school year. Picking up my transmutation eraser, sorry. So I wanted to put a little bit of stuff up here about this one. Cobalt-60 is a strong gamma emitter, that's cool, that has a half-life of 5.26 years. The cobalt-60 in a radiotherapy unit, that would be for treatment of cancer and things like that, must be replaced when its radioactivity falls to 75% of the original sample. This tells you how old the book is. If an original sample was purchased in June 2010, when was it necessary to replace the cobalt-60? The book said, when is it necessary? When will it be? I was like, when was it? So we have this equation, KT equals ln of NT over NO from kinetics. K is what's called a rate constant, and I'll show you how to calculate that in a second. T is time. That's natural log, like calculator will do it. NT over NO is the amount of a nuclide at a given time, that's what T stands for, versus the original amount. And if you read in the problem, this is going to be 0.75 or 75%. To calculate K for radioactive decay, it's always 0.693, that's always there, that's an always value, over the half-life. So I did that next. You're not going to have to do this again, but the problem came up in this section, so I wanted you to see. 0.132, and this is a weird unit, years to the negative 1. Since it was nothing over years, it'll cancel out when we solve. So, when I put this all together to solve for t, because I had a negative here, I have a negative here, so we'll do negative ln of 0.75 divided by 0.132. The years will come back up on top because years to the negative 1 is on the bottom. When I ran this calculation, I got 2.18 years. And I hate when I get decimals of years. So I did it, I worked it out. It's 2 years and just over 2 months. So it came out to that thing needed replaced in August of 2012. Some other cool stuff. I like radio tracers. Radio tracers are radioisotopes used in chemical reactions to track the products of the reactions. So you put them into the reactants and see where they come out in the products. It's like dropping something. You want to see how a stream flows, how fast, where it's going? Drop something in at the top of the stream and track it through. So there's an example here, and what I want you to look at, it's pretty quick. If you look at the reactants, you'll notice that there's an oxygen in the it's in the acetic acid. No, it's in the methyl alcohol. It's in methyl alcohol in the reactants. There's an 18 on that oxygen. So what I want to know is which of the reactants contributes to which of the products, because they all look like carbon, hydrogen, and oxygen to me. So, since they all look like carbon, hydrogen, and oxygen, I want to see where that oxygen goes. I follow the oxygen 18 from methyl alcohol into methyl acetate. We know where the oxygen went in that reaction, so we can figure out better how the reaction occurs. That's all that says. That was pretty cool. I like that. Fission versus fusion, this comes up whenever you talk nuke. Fission is splitting of a radioactive nucleus. It breaks down. 3 radionuclides that undergo fission that split, uranium-235, that's uranium-235, uranium-233, and plutonium-239. Just some examples. You see that those are 92 and above, so those are going to be your transmutation. That makes sense that they'll split down. If you look at that picture, what that picture shows was a nucleus just hanging out. We smacked it with a nucleus, and it broke down. This picture shows a chain reaction and fission. A chain reaction and fission. Who starts it? The neutron. The neutron that comes in the top. This is how nuclear weaponry works, a chain reaction. Get it started, and a lot of energy is released. This is also a way to release energy safely from nuclear sources and nuclear power plants, is to start a reaction. Fusion, when light nuclei fuse or join into heavier ones. Does this happen here? Not on its own. Where does this take place? At the core of stars. I can't make it do it. Not here. At the core of stars like the sun. Is it commonly used on Earth? Not so much. Those conditions are a little dangerous, so we don't tend to play with fusion. Fission is also dangerous when it's not controlled. At Chernobyl, at 3 Mile Island. We have to be careful. Nuclear stuff can be dangerous, but most things out there can. Fission is useful. Fusion is not particularly useful except as we enjoy sunlight. Nuclear decay.